Hi, so in this video, I would like to speak about our project from DIS on designing for embodied sense-making of mathematics, specifically looking at directed and spontaneous bodily actions, and I'll come back to that. First, there is a set of theories arguing that when we learn something new or when we explain something, we extensively rely on our bodies. So, for example, we might use our body to do something called cognitive offloading, which is keeping track of information on your body to alleviate your cognitive load. So this can be like finger counting during a complex operation. Another thing is communication. We spontaneously perform gestures when we communicate, or we might also do pointing gestures to create shared attention with our peers. We might also use our bodies to represent abstract concepts in a more concrete manner. And also at the emotional level, so we might use our bodies to calm down if we feel stressed during a learning activity. And in our work, we're actually quite interested in designing interventions that leverage those bodily actions. And we do that using virtual reality. And in virtual reality, that means we have an interactive multimodal learning environment that we interact with through meaningful movements. And there are many examples of such projects that you can see here on the panel. So that's the side on the learning perspective. Now, if we look at the interaction design perspective, there is this concept of embodied interaction. And here what it says is that interaction is informed by and grounded in its physical and social context. So if I want to design the interaction with this cube here, it's not enough to consider the user and the cube. I need to consider the physical and the social context. Why does it matter? Let's look at a concrete example. If you see this gesture, you're not too sure what I'm trying to express. It's a priori meaningless. Now, if I look at the context where this gesture would happen, for example, the smooth surface of a smartphone, then it gains meaning because with this gesture, I can stretch the digital space and compress the digital space. And I quite like this example because it's not a natural gesture in the sense that I don't go around the world and zoom on things by moving my fingers, but it has such a strong physical meaning that once I have learned this interaction, I will not forget it. So in our work, we are wondering how do we bring those two things together? How do we build this interaction that supports the learning? And in order to do this, we want to do a two-step process. So the first thing is we want to understand how learners move when they make sense of mathematics and what are the movements we should try to create in our intervention. And then the second step is how do we design interaction to support and leverage even those bodily actions? And because mathematics is quite a wide field to start with, we first focus on derivatives. So let's go back to the embodied learning framework. We have a learner that performs bodily actions to represent a concept, and from this we have learning. However, there are two kinds of bodily actions that can be helpful. The first thing is spontaneous bodily actions. So when I'm learning, I'm spontaneously performing those movements. And we look at this through a qualitative study with 6 participants, 2 being novices, 2 being experts, and 2 being teachers, who are also experts. And here we had 4 tasks, more concrete or more abstract, where students had to reason and experts had to reason about some of those concepts, and we analyze the gestures that they produce during the process. Then we also look at directed bodily actions. So here what this means is that if I teach you specific bodily actions, this will help you learn. And one of the prominent projects on this direction is the Hidden Village, where they teach students certain gestures that they'll then help them perform better proofs in geometry. What we did here is that we designed a game on derivative. If you're interested in the whole design process, there's the reference down there. And here we compare 2 conditions. One on tablet, which is lower embodiment because you have less sensory motor stimulation, less movement, and also less immersion. And then a stronger embodied condition in virtual reality. And here we did this study with 130 participants where we actually went into the high schools and did the studies with them. In the paper, we describe the both studies, but here I want to focus on the aggregated design recommendations. But if you're curious, you can check the paper for more information. So the first thing we found, which I found quite interesting, is that we should expand embodied interaction beyond position and movement. So if you look at previous framework that look at how to design those embodied interventions, they're very much focused on my body represents the concept, my body position represents the concept, or my body movement represents the concept, or an object represents the concept and the manipulation with this object it represents the concept, all these kinds of discriminations. But what we noticed in that study is that students actually relied on something else to represent mathematical concepts, specifically muscle tension. So when they were representing a slope, I was expecting that they would either use their body position to represent the slope, so like this, or their body movement, so like that. And what they actually did is often they would go up and down to show whether this is a slope going up or down. And then to express how steep it is, they would use muscle tension. So this is like a steep slope going up, and this is like a less steep slope going up. So here we can use off-the-shelf sensors to measure this muscle tension and integrate it in the design of the learning activity. Another thing is that learners spontaneously use metaphors when discussing concepts. So for example, you can see the first participant here mimicking a mountain. The second one is explaining a step-by-step increase by actually mimicking steps. And the two on the bottom row, they were mimicking a parachute in one of those tasks. So how can we integrate that in design? There's this nice paper from Kai by CUP who looked at whether we could automatically detect such gestures and create interaction based on those metaphors. So for example, if I do this, I would be able to control a bird. This is one very interesting project in that direction. Another thing we did also in this digital glove project in some of our previous work is to see if we could exploit the avatar and the representation of the person in the virtual world to elicit productive bodily actions and also create meaningful interaction. If we bring all of this together, one direction for future research would be what we call semantic avatars. So what if we could deliberately design digital avatars to generate certain bodily actions and highlight certain meanings? So for example, if I want to learn how to count in base 8, I can imagine an avatar with only 4 fingers per hand. So that's a research direction that I think would be quite interesting in the future and that we started to explore. The third thing is we noticed that people use fine gestures and coarse gestures differently. So if they want to highlight a very specific behavior at one point, they would use the pointing gesture and move very slowly to describe the curve very carefully. However, once they understand the deep characteristics of the problem, they will use coarse gesturing. So for example, hey, here there's a plateau, and they just like repeat this coarse gesture, not going that careful about the local situation. And it's quite interesting because there's some previous work showing that novices and experts move differently. So novices tend to go very carefully and focus more on the superficial features, and they use the fine gesturing, while experts will start moving more coarsely. And this is interesting from the design standpoint because, for example, in our game, we had a scoring system in the game. So based on how close you are to the solution, you would be closer or not to 100%. And what we noticed here is that the students then, they spent a lot of time fine-tuning in order to reach those 100%, which is actually not so productive for learning. So here again, this informs a bit how we should focus the design and also be a bit more careful about gamification, because what we want to go for is those coarse gesturing, which is a sign of mastery and also a sign that the students understood the deep features of the problem. Another thing we noticed is that the learners use position in space to represent certain concepts. So for example, on the top row, this teacher was explaining that the curve seems to be composed by an x square term and an x cube term. And then every time she wanted to come back to those concepts, she was saying x square here and x cube here. And there was those anchors in space that represents those concepts. And the bottom learner, what she was doing is that she had a reference point, and then she was showing the movement based on the reference point. And here, for both of those things, there's a lot that happened in the invisible space. So once they have created this anchor, it's an invisible anchor. And here, again, from the design, where it becomes interesting is what should we show to the learner and what should we let them imagine? So in our derivative game, for example, we showed some wooden handle to represent the slope at this point and to be manipulated. But actually, maybe this is something we should let the students imagine as they make sense of the concept. So here there's a question of like, what should we show and what should we let students imagine? And another thing I want to mention is considering in VR embodied learning assessments. So in our study, we looked at a math anxiety as an individual difference that could impact the results. And here what we found on the tablet condition is some relationships that we often find. So we found that students who have strong math anxiety struggled more to solve the problems, and also they had worse learning outcomes. However, in the VR condition, the more embodied condition, we didn't find those correlations anymore. We think this might be due to the fact that VR is immersive, so I don't see my peers, I don't see my teacher, and the social aspects of math anxiety are not activated. It could also be because it looks less like mathematics, but in any case, it shows us that by having in VR embodied learning assessments, we might be able to get a better accurate representation of how much people learned. And I would like to connect this to some previous work that showed that when we learn something new, we are first able to express it through gestures before we can express it through speech and before we can express it through writing. And if we think of how we evaluate learning nowadays, it's very much focused on the learning assessment, sometimes the speech, but very rarely on the gestures. And if it is on the gestures, it's very cumbersome. So someone needs to manually annotate hours of videos and make sense of this data. So what we would want to do in future work is leverage multimodal learning analytics to have real-time assessment of preliminary learning at the gesture level. And on this, I would like to take some time to thank my co-authors, but also very importantly, the teachers who made the studies possible. Again, we had 130 participants and we went in actual high school. So this was only possible through the cooperation of many teachers here in Switzerland and also their students. So I really want to take the time to thank them. And if you're curious about more work, here are some papers that you might find interesting. Thank you for your attention.